This is the Proportions and Similarities tutorial. Let's begin by discussing the multiple transversal proportionality theorem. If more than two parallel lines intersect two or more transversals, they will divide those transversals proportionately. So, let me show you what I mean by that. Here are three parallel lines, and they're intersected by two transversals. Here's the first transversal, and here's the second transversal. Now, I can tell you, because of the multiple transversal proportionality theorem, that segment GH over FG is equal or proportional to segment JK over IJ. So let me indicate those with some arrows. Segment GH here, this little segment, over FG, the length of this segment, that proportion would be equal to segment JK over IJ. Now, notice that GH and JK correspond to each other here between those two transversals. And the same thing with segment FG and IJ. They're corresponding parts of these transversals. So if you want to write a comparison, you would choose one part, like GH, and write it over another part, another segment of a transversal that you know, such as FG, and compare that on the other transversal to those same corresponding parts, the way that JK corresponds with GH and IJ corresponds with FG. So let me show you a couple problems around that. Let's say, for example, that you have these two proportions. This first proportion up top, and then we'll discuss the second proportion. Now, in the first proportion, we have segment FG and IJ on the numerators of these two proportions. So we're comparing these two parts. And the denominator of these two proportions, the left denominator is missing, but on the right, we're looking at JK. So what segment of the other transversal on the left do you think that we'll be comparing? Well, if you said GH, then you're right. We'd be comparing GH because it's directly proportional to JK, right here. Let's take a look at another example down below. So first segment we're going to compare here is segment FH. So this entire segment of the transversal on the left. So we're going to be comparing that to the entire segment IK of the transversal on the right. Now, in the denominator of the left proportion, we're looking at just GH, this segment right here. So what segment of the transversal on the right do you think that we're going to be comparing to? Well, we'd be comparing to JK on the right. So when looking at proportions, you can use what you know from the multiple transversal proportionality theorem to establish good proportions between two different segments of two different transversals. That'll give you a direct comparison between those that you can use to solve for missing information. Now let's go ahead and take a look at the Triangle Angle Bisector Theorem. In a triangle, the bisector of one angle will divide the opposite side into two segments, the lengths of which will be proportional to the other two side lengths. I have a diagram here to illustrate this theorem. So in this diagram, you can see that segment XZ is the angle bisector of triangle XWY. Now, what it's doing when it bisects that angle is it's dividing this opposite side, WY, into two segments. Now, they're not congruent to each other necessarily, but it's dividing it into two segments, segment WZ and segment YZ. Now, the lengths of these two segments, WZ and YZ, will be proportional to the other two side lengths. The other two side lengths being XW and XY. And so I've written that proportion for you off on the side here. Those original two segments, WZ and ZY now, are going to be proportionate to XW and XY. And notice how the proportion works, that this segment WZ of the triangle on the left that's been created is proportional to that segment XW. And the same thing on the right. The segment down at the bottom, ZY, is going to be proportional to the segment of the triangle on the right, XY, that we're comparing it to. Now let me give you a problem that demonstrates the use of this. I'm going to provide a proportion that looks just like this guy here. And I want you to first reverse engineer this proportion to put those values in their respective sides. For example, you know that this piece here, 7, is going to plug into WZ. So we would write 7 here. And 9 would be respective to ZY. So this would be a 9. XW we would know as 4x minus 4. And XY would be 2x plus 4. So if you were given the proportion like we were given on the left here, you could use it to fill in the values of the triangle on the right. And if you were given the triangle on the right with these values that we've just written in, you could create the proportion right here on the left if you had to. Now the important thing is being able to use this proportional information to actually solve for the value of x and therefore the missing side lengths. So what you would do in this situation is cross multiply. When you do that, you get 7 times the quantity 2x plus 4 is equal to 9 times the quantity 4x minus 4. So we'll distribute 7 times 2x is 14x, and 7 times 4 is 28. And on the right, we'll distribute the 9 through. 9 times 4x is 36x, and 9 times a negative 4 is a negative 36. Now we want all of our x's on one side of the equation and all of our numbers on the other. So I'll begin by subtracting a 14x from both sides of the equation. On the left, the 14x's will cancel, and we'll have 28. And on the right, we have 36x minus 14x, which is 22x, minus 36. Now we want to get all our numbers on one side of the equation, so we'll add 36 to both sides. On the left-hand side of the equation, we have 64, and on the right-hand side, we have 22x remaining. So now that we have 64 equaling 22x, we want to divide by 22 on both sides of the equation, and we'll get x is equal to 64 over 22, which reduces to 32 over 11. Now that we know the value of x, you could plug that back in to both missing side lengths and solve for their values. So let's go ahead and move on. And next, we'll discuss the Triangle Proportionality Theorem. That states that a line that is parallel to one side of a triangle will divide the other two sides of that triangle proportionally when it passes through them. So let me show you what that would look like. If you had a triangle like QSU and a line that's parallel to one side, in this case side QU, pass through that triangle, it's going to divide the other two sides of that triangle proportionally. So it's going to divide SQ and SU proportionally. Doesn't mean that it's going to divide them equally, they're just going to be proportional to each other. So we've established that proportionality here on the right, that side RS over side QR is going to be proportional to side ST over side TU. Notice how those two sides correspond to each other. In the numerators, these two sides corresponded to each other. And in the denominator, these two sides corresponded to each other. That's how you want to set up proportions, so that the sides that you're comparing of two different triangles actually correspond to that similar side on the other triangle. So I'd like you to take this sample problem and take a moment and see if you can solve for x, knowing what you know of the Triangle Proportionality Theorem. I'll give you just a moment. Alright, so I'm going to move on and show you how to solve for it. If you need more time, pause the video and continue and then start it up when you're ready. What we want to do here is create a proportionality just like we did on the previous example triangle. In our case, the same proportionality will work. So, we know that side RS has a value of 3, and side QR has a value of 24. Those side lengths are proportional because of this triangle proportionality theorem. They're proportional to side length ST, which has a value of x, and side length TU, which has a value of 8. Now, just use cross multiplication to solve for the value of x. 3 times 8 is 24, and 24 times x is 24x. So we want to get x alone, so we'll divide by 24 on both sides of the equation, and we'll get 1 is equal to x. So this missing little length over here, side ST, actually has a length of 1.